Good morning guys, welcome to today's worked exam answer video. Today, as per request, I'm having a look at an electrode potentials and electrochemical cells question, and I've chosen this one in particular for a couple of reasons. One, it's asking us about the weakest reducing agent in the table, and that's really common that they'll ask either about the strongest or weakest reducing or oxidizing agent. So I wanted to talk through the best approach for that. Part D is also very sneaky. We've got to put together an equation for iron reacting with different vanadium species, and the iron is going to react twice in that reaction. And then also there's a little bit of a transition metal link in here as well, because we've got some transition metal complexes in here, and there is one question on the back of here asking us to think about why the cobalt, when it has the ammonia versus the water, has different electropotential values. So that's why I chose it. I'll try to get through it as quickly but as helpfully as I can. So let's get cracking. So first question says that we have to state the meaning of the term electrochemical series. Now this table is a snippet of the electrochemical series. The only difference is this only has a certain number of half equations built into it, but the electrochemical series shows that for every single half equation. So in terms of how we can answer this question, we need to say that it is the electrode potentials for different half cells or different half equations, but the key thing is they are listed in some sort of order. So here we're going from more negative through to more positive. Sometimes the most positive ones will be at the top of the table, but either way they are in some sort of numerical order. So electrochemical series is a list of all half cell equations and their electrode potential values in numerical order, whether that's most positive to most negative or vice versa. You will see both across the AQA questions. Okay, now we then get this table, which includes a variety of different equations. They're all E0 values, where that 0 is suggesting standard conditions, and that's going to help us with the first question associated with the table. We have to state two conditions needed for the following half cell to have an E0 value of 0. So this half equation is referring to the standard hydrogen electrode, and that little E0, or the little 0 value rather, is referring to standard conditions. So we need to know the standard conditions that apply for all of these half cells, and then pick the ones that are applicable to whichever half cell we're being asked about, which in this case is the standard hydrogen electrode. And because it is the standard hydrogen electrode, we have got three options. We won't always be able to give all three, because one of the standard conditions is that the hydrogen gas is kind of bubbled into the cell at a pressure of 100 kilopascals. So that is one of the conditions that we can give. It doesn't want you to say 1 atmosphere, it needs to be 100 kilopascals. That will obviously not be relevant if you don't have a gas in your half equation. So if we were thinking about the conditions needed to make this top equation minus 0.44, please don't say 100 kilopascals because there are no gases in there. Okay. The other that we can get from the equation is the concentration of these ions. Any ions that we have in solution need to have a concentration of 1 mole per decimeter cubed. and if it's anything other than that, it will be an electrode potential value rather than a standard electrode potential value. And then the third, which doesn't connect to the equation in quite the same way, and I know it says only 2, and please do only give 2 if you're asked in an exam question for a specific number of conditions, but as I normally do, I want to give all the options that you can have. So the third would be 298 Kelvin. And that kind of applies across the half cell. So yeah, the little naught, standard conditions, and anytime we change these standard conditions, let's say our concentration of H+ ions was 0.5, it wouldn't have the little 0 after the E, it would just be an E value, an electrode potential value, rather than a standard electrode potential value. Okay, right, next one, this is a bit tricky. So for the next one, we are identifying the weakest reducing agent in the table above. Now, I'll have spoken about this before. Anytime it says oxidizing or reducing agent, I always come back to the definition. So a reducing agent will reduce another species and it will itself be oxidized. And that's the first thing that even now, with all of my experience, I still need to write down when I'm doing a question like this. So it's itself oxidized, and then when we're thinking about the weakest either reducing agent or oxidizing agent, the way I see that is it doesn't want to be oxidized. So that means it's not going to be a very good reducing agent because it's not going to give away its own electrons very easily. If it said strongest, it'd be the other way around. It would be the thing that wants to be oxidized the most. So this word here is just as important that we understand how to apply as reducing agent. So the weakest, and of course, this probably isn't an exam worthy answer, but we don't have to explain it, we just need to identify. So it doesn't want to be oxidized. And then this is where we need to know what the positive and the negative E0 values tell us. So the positive values show that the species on the left hand side wants to be reduced, and the more positive the number, the more it wants to be reduced. So in this table, the thing that wants to be reduced the most is the cobalt H2O6 3+. And negative values suggest that actually the thing on the right hand side wants to be oxidized, and the more negative, the more this species on the right hand side wants to be oxidized. If something therefore doesn't want to be oxidized, we're looking at the species on the right because that's the thing that will be losing electrons, but we want to pick it for the thing that has the most positive E0 value, because this cobalt H2O6 2+ is really not going to want to be oxidized because this cobalt H2O6 3+ really wants to be reduced. So that means that this isn't going to give up electrons very easily, and therefore it's not going to be able to reduce something else very easily at all. So the biggest mistake that I see with questions like this is that people will pick the right half equation, but then when they're thinking about reducing agents, they won't pick the species on the right hand side, which is the thing that would be oxidized. They'll just pick this species, but that is being reduced, and all of these are always written in terms of reduction. And so make sure if you're thinking about a reducing agent, you're picking something from the right hand side. What I wouldn't advocate doing is going, the weakest reducing agent is always the species that appears on the bottom right, because these values, as I said earlier, sometimes will be from most negative to most positive, but sometimes they'll be the other way around, and that will catch you out, and it is far better to be able to figure it out using the definition like I've just done there. Okay? Now, hold on to your hats, everyone, because part D is not a very nice question. It's sneaky because it doesn't, this doesn't happen very often. So it is something you have to watch out for all the time, but sod's law, the time that you don't look out for it is the time that it will appear, and there's no kind of indication in the question that we need to think about the ion reacting twice. So we have to deduce an equation using the half equations for the reduction of VO2 plus to form VO2 plus very subtly different. We got 2 oxygens and a single positive charge versus 1 oxygen and a 2+ charge, and that is being reduced in an aqueous solution by iron. So any question like this ever, I would always now be finding those species in my table. So we've got my VO2 single positive charge there, and that's going to be reduced to the VO2 plus there, and that has a value of +1 volts. And then I'd be finding my iron. So because we are reducing the VO2 plus, that equation needs to go forwards, because that shows reduction, that shows the VO2 plus gaining the electron. So we need the iron to be on the right hand side so that that equation can be flipped to go backwards to represent oxidation. Now iron in its pure elemental form is there, which is good, that's on the right hand side. It's also good because that has a negative E0 value, whereas the vanadium one is +1, and that suggests reduction, this suggests oxidation, and that's the way it's going to work. So that's going to be working in the reverse direction for oxidation. Now, why is this so sneaky? Because once we make the FeH2O6 2+, what we also need to spot is that that appears in another row of the table. So the iron will be oxidized to FeH2O6 2+ ions, but then those FeH2O6 2+ ions can also be oxidized to FeH2O6 3+ ions. And how do I know that that's going to be possible? Well, I need to check the E0 value. So for this second oxidation process, the value is 0.77, which is still less positive than the reduction value of 1. So this will be oxidized as well, because that reaction will still give us a positive EMF, and the value for reduction is more positive than the value for the oxidation. So the iron will actually be oxidized twice, whilst the vanadium is reduced once. So when it then comes to putting together the half equations, we've got quite a few things to do here. First of all, these will need to be written the other way around because they're oxidation. Secondly, we're going to have to combine these two together to give us the overall oxidation that's happening. Then we have to combine it with the reduction half equation. So there's kind of 3 steps we're going to need to do here. So the first thing that I'm going to do is I'm going to combine the 2 oxidation half equations. So I'm going to write them the right way around, and I'm going to cut out the state symbols to save myself some time. So Fe plus 6H2O will make FeH2O 6 2+ plus 2E minus, and then those FeH2O 6 2+ ions will be oxidized to FeH2O6 3+ ions by losing another electron. So by combining these two together, the intermediate FeH2O6 2+ ion will cancel, which is going to then give me the equation to show how the iron can be oxidized twice to give FeH2O6 3+ plus a total of 3 electrons. So that is now my oxidation half equation that I then need to combine with this reduction half equation. Now, in order to do that, I'm going to have to balance out my electrons. So 3 electrons being lost, so I'm going to need 3 electrons to be gained. So I'm going to need to multiply this equation by 3. So we're going to have 3 VO2 plus 6H plus 3 electrons, which will then get them to cancel, and then 3 VO charge 2 plus and 3 waters. And by writing that out multiplied up before I combine it with the iron half equation, it helps me in two ways. One, I'm less likely to make mistakes with multiplying these things up whilst trying to combine it with this one. Secondly, I can now see that I've got 3 waters here and 6 waters here. So I can scrap the 3 waters on the right hand side and bring the number of waters on the left hand side down to 3, and I can do that all in one step. So my overall answer, which I'll do in green, make it a bit clearer, we are going to have Fe plus only 3 H2O, because they will cancel, and then that will bring that number down to 3, plus 3 VO2 plus charge plus 6 H plus is going to give Fe H2O 6 3 plus 3 VO 2 plus. And as it would be the case for just combining two half equations together, we should still have all the same number of atoms on each side. We should have the same charges on each side. So I've got 1 iron, I've got 6 H's plus 6 is 12, and I've got 12 H's here. I've got 3 plus 6 oxygens is 9, I've got 6 plus 3 is 9, and I've got 3 vanadiums, and I've got 3 vanadiums. Charge wise, I've got 3 pluses and 6 pluses, so 9 plus, 3 plus, plus 3 lots of 2 plus, 6 plus 3 plus is 9 plus. Shows that I've more than likely done it right. Okay, so what I would recommend, particularly when we've got transition metals, because we know they have variable oxidation states, is always look whether the product of your oxidation appears somewhere else in the table and can it be oxidized again. Or same for the vanadium. We know vanadium can be reduced further than this, so sometimes it might be that the vanadium can be reduced again to V3 plus by the same reducing agent. It won't just be the case for transition metals, but knowing they have variable oxidation states, that's what I would look out for. Okay, horrible question over. Next one. Use the data from the table to explain why cobalt H2O6 3 plus will undergo a redox reaction with Fe H2O6 2 plus, and then we also have to give an equation. So when it says use data from the table, this is where we're going to have to say, oh, the E0 value here is more or less positive than the E0 value here. Okay, so again, I'm going to find where these are in the table. So CO H2O6 3 plus is on the right hand side there. So that's going to want to undergo reduction and go that way, gain an electron. And then the Fe H2O6, which I've already highlighted annoyingly, I'll underline in the pink, or go round in the pink. That is on the right hand side of our equation, and that is therefore going to want to be oxidized. And does that work in terms of the numbers? Yes, it does. The more positive one is where reduction needs to be occurring, and the less positive one is where oxidation needs to be occurring. Now, we don't need to use inequalities to explain this, but the mark schemes tend to like it, so my advice would be to write it in the way that the mark scheme does, so that the examiner can very easily see, yeah, got it, rather than having to try and work out whether what you've written in words matches the inequality. So we need to say that this half equation has an E0 value that's more positive than this one. So I'm just going to write that the E0 brackets, and then we write the species before reduction, and this is a bit annoying in this case because we've got these transition metal ions, but never mind. And then the product of that reduction would be the 2 plus version, and that is more positive than the E0 value for the Fe H2O6 3 plus 2 Fe H2O 6 2 plus. And that's enough for your explanation. It uses data from the table. 1.87 is more positive than 0.77, written like that. Like I say, you can do it in words, and you can say like the half equation for this becoming this is more positive than the half equation for this becoming this, but that's how a lot of the mark schemes will present that. I will add for your context that 1.81, sorry, is more positive than 0.77. And then in terms of the equation, again, the oxidation half equation needs to be flipped to go the other way. The electrons are already balanced here, so you may feel confident doing this all in one. You may not. It's completely up to you. If you want to rewrite the oxidation equation first, the right way around, then combine them, go for it. I'm a big fan of that. I'm going to try to do it all in one. So, wish me luck. So we're going to start with the cobalt 3 plus ions. They're going to react with the FeH2O6 2 plus ions on this side, and then we are going to get, as our two products, the cobalt ions are going to be reduced from 3 plus to 2 plus, and the iron 2 plus ions are going to be oxidized to iron 3 plus ions. Atoms quite clearly balanced charge wise. +3 and +2 is +5, +2 and +3 is +5. Okay, and then finally the little question on the back: suggest why the two cobalt 3 complex ions in the table above have different electrode potentials. So cobalt 3 complexes, so we've got the one with the water there, and we've got the one with the ammonia there. The cobalt one has a value of +1.81. The water with the cobalt is +1.81. The ammonia with the cobalt is only +0.11. So quite significantly different actually, even though the cobalt's in the same oxidation state. One of the things that we do need to know is that the ligands we have attached to the transition metal complex affect the electrode potential values. Now this is a suggest question as well, so even though you are supposed to know that according to the spec, if you're not sure, you can kind of look at what's different and go, well, the only thing that is different between them is we've got different ligands. It's not a different coordination number, because water and ammonia would give us a coordination of 6. But they are different ligands, and ligands will affect the size of the electrode potential. So all we would need to say is different ligands. And that, in lots of ways, is a nice tie-in with transition metals and electrochemical cells. Obviously not nice if you're the one doing the question. Hopefully I've made sense, but as always guys, any questions, please do hit me up. I'm always more than happy to help. Thank you so much for watching. Hope the revision's going all right.